Good morning, everybody, and welcome to week 6 of Astronomy 120. This is for basically this is after the exam, so we are actually still building up stuff now for the next exam. We are still dealing actually with the solar system. We introduced it last time, and basically what that is we initially basically what we were concerned with is the time and how we locate objects in the night sky and so on and so forth, and the different approach we had for the solar system in general, for the stars in general, how they classify and so forth, so on and so forth. But then we're moving specifically, we moved actually already, we did that to the solar system. So in doing so, we said, okay, what is the most familiar object that we can start with? Obviously, it's the Earth. So we dedicated actually a whole 2 units just for the Earth. We looked at the Earth from the vantage point of that of a solid sphere, if you wish, made up of solid materials, and that turned out to be have different different interesting structure in the sense that it has the 4 layers, basically big layers, namely the inner core, the outer core, the mantle, and the crust. And then in addition to that, we saw some differences even in the crust itself. For example, you have thick areas near the continents and also thinner areas where the oceans are. And then we saw the plates and how the plate tectonics explain a lot of the things that have to do with the weather, how the Earth evolves overall. The Earth is a dynamic object in the sense that it continuously changes with time because of the different weathering phenomena that is associated also on its surface, and as much also as in its surface. We saw how the planet evolved. We have mechanisms for it to study it. It's up and close to us. We use earthquakes, seismic studies to basically determine its structure. We also use radioactive dating to determine the age of different components of the Earth. So we have a wealth of methods to basically gather all of this information, and we have an understanding of how the Earth works, at least in terms of the solid sphere. Solid sphere is just one component of the Earth, but there is also the atmosphere. Starts with the hydrosphere, which is an essential component also of the Earth, namely the Earth is mainly water. Then on top of that, you have the atmosphere of the Earth that is also influenced by all kinds of phenomena and all kinds of sources. One of them is the sun, of course, that heats up the atmosphere, and that causes the atmosphere to move around, and that also adds to the changes onto the surface of the Earth. The Earth also, or at least the atmosphere of the Earth also is influenced by what's going on inside the Earth itself, namely the magnetic field of the Earth, and that too has different implications on the surface of the Earth. On the atmosphere of the Earth, namely the ionosphere, for example, the particles that come from the sun are directed to specific locations that could yield to auroras. The structure of the atmosphere also plays a major role in terms of protecting the Earth from the meteorites and also from rays that are coming from the sun mainly, and also cosmic rays. So this is basically the stuff we learned from the Earth. We're going to take that knowledge and try to expand it to see how it applies to other objects in the solar system. Obviously, the next object that we're going to be focused on is another object of the solar system named the Moon. The reason why the Moon is of interest to us is because it's a close-by object that we have seen from day one. Basically, as a human started to record history, they recorded its existence, and it's a big dominant object in the night sky. And even daytime, actually, you can see the moon, and people start taking notice, and then immediately they associated its motion with all kinds of human activities. One of the things that turns out to be a useful thing is to keep track of time, because the moon goes through different phases, and that is a way of actually keeping track of time. As a matter of fact, the word month originates from the word moon itself. So that should give you the connection between human activity and civilization in general and astronomy in general, but also specifically with the case of the moon. Now, the moon is an interesting object by itself. It was an interesting object from antiquity until today. There's missions that, ongoing missions right now. The biggest mission, of course, Artemis mission from NASA that was tried to launch a few weeks ago, and then because of weather and also because of technical issues was delayed. But we're hoping to continue that process. This is not the start really of the exploration of the moon. It started a long, long time ago, as a matter of fact, from the 60s to the 70s until today, continues into today. So the moon is an interesting object in the sense that we had actually manned mission to the moon. In other words, a human being actually landed on the moon itself, on its surface, and brought us materials from the moon to the Earth. And that is tremendous opportunity to see the structure of the moon similar to what we saw the Earth. For that, we saw that the moon, for example, has similarities with the Earth in terms of composition. So that was actually an interesting object by itself, okay? So we needed to understand where these similarities are coming from. Of course, there are differences between the Earth and the moon. So that is one thing that we need to understand. How come we have similarities and differences in terms of the composition? So that when we brought stuff from the moon. Then the other thing also, there are obvious structure in the moon itself. When people looked at it, actually the first person who used the tool to look at it was Mr. Galileo. Before him, again, you could see clearly that there are different features on the surface of the moon. There are darker areas and brighter areas. Now we know that the darker areas are lowlands and the brighter areas are highlands, basically. It's like a mountain reflecting light from outside, from the sun, where it's sitting higher, so it's going to reflect the shaded area, which is inside. That is actually the lowlands of the moon. So that's what we know today. As a matter of fact, it was Mr. Galileo himself, when he used telescope to look at the moon, one of the arguments that people presented before him was the reason why we have all kinds of features on the surface of the Earth in terms of mountains, hills, and also valleys, and in terms of canyons and so on and so forth, is because due to mankind sinning, therefore the Earth is not perfect because they sinned on it, so they ruined it. Basically, that's what the belief was. And this is actually the belief that preceded Christianity, so it's not necessarily linked to its origins to Christianity, but later on it was adopted actually by the church. So that was a problem, because then immediately when Mr. Galileo looked at the moon, he saw similar features as the Earth does. And that was one of the reasons actually to support Mr. Kepler's laws, in a sense that the circle is not perfect. And again, for the same reason that was thrown for the circle was also put for the shape of the moon. So he immediately refuted that with solid observations that, look, the moon presents similar features in terms of lowlands and highlands. And you can clearly see that with a telescope, small enough telescope that he was, or at least large enough telescope, I should say. It was a small telescope that he was using. It was a toy, I guess, that he modified to look at the stellar objects. So again, this is some of the features. One of the big features, if you had a chance to go and look at the moon, and actually lately, and I know you guys have a ongoing project right now for lunar observations. The first observation you should have done already on yesterday. No, or is it the day before? Yesterday, yes. And then you have another second observation that is coming this coming Monday. So if you did really your observation and you saw the shape of the moon, you would tell, okay? And it was visible even to this morning. I mean, I went outside to charge my car, and basically the moon was still full moon. So that's basically what they should have seen. There are some features in addition to the fact that you have the bright sides of the moon, bright areas of the moon and dark areas of the moon. There are other features. There is a craters that you can clearly see craters, and with craters there are some basically emanating lines from it. So that is actually the Tycho crater, the biggest one of them in the southern part of the moon. So these are features that we can see even with the naked eye. We really don't need a telescope to see that. Okay? We don't need binoculars to see all of these features, although those tools really bring up the object a lot closer to us than what it really is already, which is very close. So the moon is an interesting topic by itself, because it helps us step outside of the Earth, take what we know about the Earth, try to understand what's going on with the moon, and then actually later on expand it to the solar system. It turns out, and we will talk about that more down the road, the moon is actually an odd thing in the solar system. Earth's moon, that is, okay? Earth's moon is an odd object in the solar system. Because if you think about it, Venus, which is an inner planet, does not have a moon. Mercury, which is an inner planet, does not have a moon. Mars, which is an inner planet, has two tiny rocks, actually, asteroids, that it captured and became its moons, but they're extremely small, of irregular shapes. They are not spherical shape like the moon, the Earth's moon is. Earth, on the other hand, has a big spherical moon. So that stands out completely in the solar system. So in addition to the structure of the moon, as I was saying in the beginning, that has some similarities and differences from the Earth, it is its presence actually that is kind of a question mark that needs to be answered. How come the Earth has a moon? And this, of course, holds true for all of the inner planets. The outer planets, on the other hand, are bigger and they have moons. As a matter of fact, Jupiter has some 70 odd moons, and every time we discover new moons, so the number is not really fixed. Same thing for Saturn, same thing for Uranus, although Uranus and Neptune has a lot less moons than Jupiter and Saturn, but they do have a lot of moons. Okay, so the outer planets have moons, and they have plenty of them, and there will be a whole unit just dedicated for that topic, which we're going to be exploring down the road. But the point being in here is that the Earth has a moon, and that is a question that needs to be also understood and answered. How come the Earth does? It is actually a good thing for the Earth to have moon. Without it, most likely life would not have evolved on Earth, at least life as we know it. Because one of the things the moon did was it regulated the seasons on the Earth. It really helped the Earth basically stabilize. If the Earth did not stabilize and went through extreme temperatures and extreme conditions, like a lot of objects are out there, then it would not be able to give time for life to evolve to a form that is continuing basically to build on the previous stages. Because every few years, there is a devastating event that causes the entire planet basically to shift from one side to the other. That is not long enough time for a planet to sustain life. As a matter of fact, you don't really need years. If a few decades, a few centuries, even a few hundreds of thousands of years or millions of years, a big event happens so that there is a extension of the big on a larger scale than what we have seen, then of course life would not have time to evolve. Okay, as a matter of fact, life has evolved in the beginning from its form, from its microbial form to its multicellular form. It took billions of years. So for the most part, life on Earth was a unicellular life, basically. It was microbial life, that's all. And that is how life evolved on Earth. But because the Earth was helped, among other things, that's not the only reason though, among other things, by the presence of the moon, it was given enough time for life to evolve into a more complex form that we know it today, that we see it today. So that's basically the idea. Of course, when people talk about dinosaurs and all of the life that was before us, dinosaurs are only 65 million years ago. It's not really that far away. I mean, relatively speaking, of course, 65 million years is still long. But compared to the age of the Earth that we saw from the previous units, which is 4.5 billion years, that is nothing. That's a drop in the bucket. Okay, so this is basically the idea behind this unit regarding the moon. So we need to understand it, and hopefully it's going to be also a stage toward learning other things. So again, this is a technique used by scientists a lot, especially in astronomy. They use that, and it's borrowed honestly from physics that has this approach of step by step, and later on it was expanded into all kinds of science, not only science, actually other fields of human activity and knowledge like technology and even other problems that you would want to solve. So it's this approach. So again, we started with the most familiar. Now we're moving to something less familiar, less tangible. I mean, yes, we sent landers on the moon, we sent orbiters on the moon, we sent actually probes to the moon, we sent actually manned missions, and that's the only object that so far in the solar system that has that distinction in the sense that humans actually landed on it, other than the Earth, of course. That's the other object that we know firsthand. So that is another thing. Then after that, for this week, we're going to move into Venus. And again, there is a reason, a rationale behind the choice of Venus, because if you look at the book, there are all every unit is now dedicated to a planet. So basically, you could spend the entire semester just talking about the planets in the solar system, and that is just one topic. I mean, one course. So we don't really have the luxury for that because we have other things also to study. We have other things in the solar system to study too. We have moons in the solar system. We have dwarf planets. So if we're going to dedicate that much time for every single object, it's not going to be enough for right now. So again, we have other objects that we need to focus on in the solar system. So we need to really decide. We need to make a call for it. So the distinction here was made for Venus, and there is a reason for it. And the reason for Venus is because it has similarities with Earth and also has differences with the Earth. So we want to understand, I mean, Venus is referred to as the twin sister of the Earth, but you will soon discover that it's really not a nice twin. In a sense, it has conditions on its surface that are completely unbearable for life as we know it. Because its surface temperature is the hottest object in the solar system, period. It's hotter than any other planet in the solar system or any other object in the solar system, of course, other than the sun. Okay. Then its atmospheric pressure on the surface is tremendous. It's about 92 times bigger than that of the Earth. So we want to understand here is something that is similar in size to the Earth, similar in mass to the Earth. We believe also similar composition to the Earth, evolved in the same almost time as the Earth did, but something that went completely south, does not support life altogether, to something that is 100% basically hospitable and actually favors life, and life evolves on it. So evolved on it and continue to thrive on it. So that's basically what we want to understand. That's why I chose personally actually Venus more so than Mars. Also, Mars attracts a lot of attention from projects and things like that. But Mars is actually smaller in size. But we're going to make comparisons. We're going to compare the two to see basically which one is at some point. Okay, for example, we'll talk about the composition of the atmosphere on Venus, and that of we're going to bring up to the picture of the atmosphere and Mars. We're going to talk about the surface of Venus. We're going to talk a little bit about the surface of Mars. So we're going to bring Mars. So Mars is not completely basically forgotten, but it's somewhere in the background. Okay. So let me share with you the screen first for what's going on this week, so that we have a full understanding of the topics that are covered and so on and so forth. So let me bring up the this week first, week 6. Okay, so share. Okay, very good. So here is what we have in week 6. Again, stuff that you guys now are accustomed to. You see more or less on a lot of basis, which is not on all the time. Every week has its own objectives. And if I click on the objectives again in here, you see a bunch of stuff that is listed. You have, of course, a discussion from the previous week, this week's discussion. You have a quiz actually also that is due on, this is wrong, it should be, okay. It's the October 22nd is not a Saturday, it's a Sunday actually, okay? No, it's a Saturday, I'm sorry. Did I say, let me double check just to make sure. Yes, it is Saturday, very good. So it's a Saturday, so this is correct, I'm sorry. Okay, I thought it's a Sunday, 21st is a Friday. So everything is correct. So you have all of these assignments that are due on these dates. You have a homework assignments that is due on the 29th. So it's not next weekend, it's the weekend after. So you have a little bit of time on it. It's kind of a lengthy assignment, honestly, and I'm going to talk about it specifically. And we're going to have a discussion on it. So I really want you guys to understand what's the rationale behind it, because it has some interesting discussions in that homework assignment. One of the current studies that basically was published, I think about 2 years ago or so, basically suggests that Venus was in similar conditions to the Earth, albeit slightly hotter than the Earth because of its proximity from the sun. But it had oceans, it had land. It was similar to the Earth in terms of at least it looks outside similar. Okay, so the question in here is how really similar that was in terms of how much water really did it have. Okay, so we're going to find an upper limit of how much water it could potentially have, and you will see that it really did not have much water to begin with, but it did. According to the study, 150 million years ago, from 150 million to 500 million years ago, the planet was actually similar to the Earth. But something happened from that time until now. So the study was kind of, usually there are errors with studies anyway, they have to contain them. And this is what we saw for those sitting in Astronomy 125, that when you do measurements and when you do calculations, usually you have errors. So it has that margin of error, which is kind of big, but that's fine. The thing with it's 500 million years ago to about 150 million years ago, before that, the planet was similar to the Earth in every which way. Something happened to it, though, that evaporated all of that water. I mean, right now, there are speculations, basically the models that we have, maybe it was hit by a big asteroid, and that asteroid triggered a bunch of volcanoes, that those volcanoes erupted every which way, and those volcanoes basically built up that thick atmosphere that is led to the greenhouse effect that was basically went to extreme condition that raised the temperature an unbelievable level that evaporated all of the oceans and the surface of the planet, and now the planet the way it is. The other part of it also is, and that you have to take account of the fact that the sun, as it ages, it grows in size. Okay. And as it grows in size, this temperature becomes hotter and hotter on the objects that are nearby in it. So a young sun would not have emitted as much heat to the young planets, basically whether Earth or Venus, but as it evolves, as it grows, that is one of the things that would have happened to the sun in the sense that caused it. So in homework 4 is an interesting homework, and I encourage you guys to again, strongly do it, so because you're going to be graded on it, first of all, okay? And because also we're going to have the discussions on it. The other part also that is due this week is the lunar observation. You guys should have done already the first lunar observation, which was yesterday. And you should have noted all of the things that had to do with the basically the different components of the assignment. But then also you will have another one this coming Monday, which means on Sunday, October 16th, is that Sunday? Yes, October 16th is a Sunday. So on Sunday, you're going to go out and look at the moon and see its position, document your observation, just in case if Monday is has an inclement weather in it, so that you can guys go and do your observations on Monday. Or if Monday is, you cannot do your observation, obviously Tuesday, October 18th is still the other option to do it. But that's the window for your second observation. So these are the stuff that is due this week. Units 39 and 41 are the ones that are going to be discussed this week. And unit 39 deals with the moon. And this is basically a full moon, one of the nice pictures that is taken by, I think, NASA. But it shows the main features of the moon, really. The dark surface area of the moon and the bright areas of the moon. Mr. Galileo concluded that the dark areas must be lowlands. And he called them Marias. Maria in Latin means basically water, in mer in French. I think there is similar probably word for it in Spanish, which stands for not ocean, sea, okay? So that's the translation for it. And this are dark area. Now we know basically what happened in here. When the moon was hit by asteroids, what happened in this case, the young moon that is, the lava that was underneath the crust of the moon basically poured out. And as it poured out, it gave this smooth surface, and the smooth surface basically hardened over time, because the moon did not have a lot of heat in it to begin with, because it's smaller in size, and also because of it does not have a lot of geology on it anyway. So basically it hardened and gave you this dark areas in it in the lowlands. This is from the impact that was happening on those places. So the moon, at least on this side, looks kind of heavily impacted by those early collisions. But if you look carefully in here, even on those surfaces in here that are smooth, there are some spots in here that indicates bombardment that happened later on. So yes, there is actually activity in the beginning that is left its traces on the surface of the moon, but there is actually later activity. And on the surface in here, in the bottom right of the picture, you will see a huge crater. That is actually what is known as a Tycho Brahe in honor of Mr. Tycho Brahe. A lot of observations. So this is the moon. The next unit actually deals with Venus, and I already gave it enough introduction up to this point to talk about Venus. Most likely we're not going to be able to do that today. But that's basically the topics of this week that we're going to be covering. And then we have the discussion that is due on Friday, October 21st. And then we have the notes, again, for 39 and 41. And then here, actually, it's today that popped up for me, this link from NASA. It was published October 4th. And so I received this notification from NASA, basically YouTube channel, that they have a new simulation for the moon. And I actually encourage you to watch it. And it's a very short simulation. I think it's about 2 minutes or so. It shows you how the moon basically was created through a collision between a Mars-sized object. Now they give it the name Theia, and that object basically hit the Earth at the right angle, causing the moon to form. Part of that collision basically formed the moon, of course. And that's really the theory that we're going to be working with. So there are all kinds of trying to understand where the moon came from. Again, as I said in the beginning, the moon is an odd object for the Earth. Look at Mars, does not have moons really to talk of. It has couple of objects that are not really moons, captured asteroids, Phobos and Deimos. Okay, and then you have Venus has none. Mercury has none. The Earth has a moon, and it's a big moon. So we needed to understand where that thing came from. And again, that's why we were proposing, and all kinds of theories were proposed to try to understand where the origin of the moon is. So we want to understand that. So that's what the purpose of that video is, that I posted in there from NASA, that I'm hoping for you guys to look at and watch it. And again, it's a simulation. So what a simulation is that you basically put stuff on a computer. So you go and program stuff on the computer, and the computer will spit out all kinds of data back to you. And of course, if you're familiar with any experience with any kind of programming, the computer basically deals with numbers. It doesn't give you visual stuff. So you take those numbers and you make them into what looks like a visual. So the simulation shows you two big objects, albeit both of them are smaller than current day Earth. One of them is of the size of Mars, the other one slightly smaller than the Earth. So when they collided, the bigger object, which is the Earth, basically stayed, most of the parts staying in its place, but then it recaptured some of that stuff from the Mars-sized objects, and the difference is the current moon. So this is the simulation we have. So this corresponds to an interpretation of the fact that the Earth has a moon, number one, and then also interprets some of the things that were also collected, the data collected from the observation of the rocks that were brought from the moon, because those rocks show similarity to the Earth from the moon. So during that collision, parts of the Earth from that collision also were transported and put on the new moon that formed. So that explains the similarities. But also there are differences enough so that the moon has rocks that are different than where the Earth is, because they came from Theia, basically. So you're asking, what happened to the objects that fell on the Earth from Theia also? Wouldn't show that also the same thing and complete everything with the same thing, same structure, similarity in both ways? No, not that much. The reason why, the prelude to the Earth, if you wish, the bigger object that was a part of the two, was bigger. So most of the stuff right now, most of the Earth stuff is from the planet that was in here, that is what we call today Earth. So that is one thing. The other thing also is the heavy stuff from Theia, namely the denser material. Remember the Earth, the process, this happened when the Earth was still cooling down, so it was still hot. So using the idea of the differentiation, basically, namely the heavier object, the more denser object will fall inward to the core of the Earth, and the objects that are lighter will stay outside. So that's probably what happened to it. As a matter of fact, there's a new study now to try to map the core of the Earth, the solid core of the core of the Earth, the inner and the outer. So what happened was, now we saw that, at least the current studies are being published right now, that it is not a smooth surface. In a sense, it's not a sphere. There are some protruding components of it, stuff that is coming out, basically, especially in the area near South Africa and Australia. That area in there shows that there is an object in there that is actually sticking out from the core. So that explains perfectly then this collision, because during the collision from the Earth and the Theia, the part that went in, the heavier part is migrated to the core, and it's still migrating. So it's still not a completed process. So that collision that happened billions of years ago, it's still an ongoing process, really. So that perfectly explains the situation, whether the lunar, the moon's actually composition, whether its presence to begin with. There is another issue also that needed to be addressed, and that is the moon in the beginning was closer to the Earth. Today we know it's receding every year from the Earth. It's moving away, making the day longer and longer. At some point when the moon and the Earth formed, the day on the Earth was about 10, 12 hours. And the day now starts to extend to current day 24 hours. And every century, the day on the Earth actually slows down further because the moon is moving away from it, from the Earth is. So in this case, it's actually causing the Earth to slow down because, again, remember when we talked about how the solar system formed, how kinetic energy and potential energy exchange, two objects far away from each other, when you bring them closer, they move faster. Just like a ballerina, when she brings her hand, she will spin faster. So a similar thing. So when two objects come closer, they lose potential energy, because when they were far away, they have more potential energy. When they are closer, they have less potential energy. In favor of what? In favor of kinetic energy. So the object will move faster. But what, in this case, it's the opposite. The moon is moving away from the Earth. So it's actually gaining potential energy. Gaining potential energy on the expense of what? On the expense of kinetic energy. So that causes it to move slower and also causes the Earth to spin slower. So in this case, the day gets longer. So this is basically what's going on. So this is perfectly explained now with this Theia collision. So when the collision happened, of course, the byproducts were closer to one another, but then they are receding now, okay? They're moving away further and further. So this is actually a perfect explanation for everything, which brings me to another interesting point in here, if you think about it for a moment. Lunar eclipses, solar eclipses that we have them today are actually a luxury for us because the moon perfectly hides the sun. Millions of years from now, that is not going to happen. The moon will be far away to a point that it's not going to cover the entire sun. So during a lunar eclipse, solar eclipse, you will still see the sun basically on a big, like a ring around the moon. So that is actually, we are in a golden time of this event, at least, which brings me to another interesting point. Are all the moons going to cover the sun on every single planet out there, whether it's a solar planet or an extraterrestrial planet? That's another question, okay? Again, we happen to be on a moon whose ratio, the ratio of its size over its distance is the same ratio of the size of the moon to the sun to this distance to the sun. So this is actually an ideal situation. Ratio 400 to 1, take the distance of the Earth moon divided by the size of the moon, take the Earth sun distance divided by the size of the moon, it's the same ratio. That's why you have perfect solar eclipses at this point, okay? But then the moon is moving away. So again, these are the units in terms of idea in general. So let me see if I can get the topic in here for you guys. Okay, I know the introduction took everything, but hopefully you guys have a better understanding of what's going on now. So again, explain how formation by major impact can explain the moon's composition as well as other unusual lunar properties. Okay, describe the surface features of the moon and its internal structure. Okay, when we talk about the internal structure of the moon, really we are coming up with some sort of a theory based on our understanding of the Earth's structure and based on the ratio of the size of the Earth versus the size of the moon. Okay. And the fact that we don't absorb tectonic plates on tectonic motion on the moon like we observe it on the Earth. So we're going to make an assumption also based on that, how thick the plate is, and also if in case there is a plates at all. I mean, at least the crust, how thick the crust is. Explain how craters and also mareas formed and why the moon has no atmosphere. Of course, the moon's gravity is tiny compared to the Earth. So whatever atmosphere it had, because here is the thing, the Earth and the moon formed in the same stuff. So initially, the moon had also outgassing, namely producing atmosphere also from its volcanic activity, but also from the materials that is smashed on its surface from the early bombardment. So that must have also formed the atmosphere, but it could not retain it because of the fact that it is too small. Furthermore, it does not have a magnetic field. It may have had in the past, but it would have lost it because, again, it did not have enough heat inside to sustain that magnetic field. So it would not be able to basically deviate the particles, the fast-moving particles, to one pole or the other. So the particles will hit the atmosphere from every which way, basically stripping the atmosphere of the moon. And that's the same idea, basically, behind the same rationale, I should say, for the case of the moon versus also Mars. Mars is actually bigger than the moon, but it hardly has any atmosphere whatsoever for similar reasons. Mars is smaller. Mars does not have enough gravity. Mars lost its magnetism also early enough so that it does not deviate the fast-moving particles, the charged particles that come from the sun, and that causes its atmosphere to be depleted. Basically, could not really resist the push from the atmosphere of the sun, versus the Earth, for example, which is big enough that it's still outgassing. It still has volcanic activity or producing, basically replacing its atmosphere as it's basically depleted. But also the Earth has a bigger gravity, so it can hold on more to its atmosphere. Furthermore, the Earth has a magnetic field that helps it retain its atmosphere because it deviates the fast-moving particles one way or the other. And you're asking what's going on with Venus. Venus does not have a magnetic field because it's moving so slow on its axis. Then Venus actually has similar strong gravity as the Earth does, or at least slightly less than that of the Earth. But Venus's advantage over the Earth is that it has a ridiculous amount of outgassing. Basically, it's producing far more atmosphere than the Earth is. So that's why the Venus has far more atmosphere than the Earth, which presents a bigger layer actually protecting the inner structure in there from the sun. But that's really what the situation is. So that can explain, that can answer that question basically quickly. So explain how, describe the moon's orbit and rotation and what makes the moons unusual, okay? So these are some of the stuff that we talked in the introduction. So again, a successful theory must explain the moon's composition and orbital properties, in a sense that how come the moon has similar structure to the Earth, and in the same time different structure than the Earth in terms of composition, okay? And in terms of orbital properties, of course, that it's moving away approximately about 4 centimeters per year, basically, from the Earth. So at some point it was a lot closer to the Earth than what it is today. So many theories have proposed about the origin of the moon. So there is an idea that the moon was captured object, that it basically similar to Mars, okay? Mars captured 2 tiny moons, and those 2 tiny moons are actually different in every which way than Mars itself. So that fits perfectly. Would the moon also fit the bill? No. The moon's composition is too similar to the Earth for this to have happened, basically. So they are too similar. So they must have shared some joint history in the past. And the twin theory says that the moon and the Earth actually formed in the same time. But they actually have a difference in composition enough so that that's not actually correct. So it could be a hybrid of the first 2, okay? The expulsion theory, Earth spun very quickly early in its history, and throughout a chunk of it that formed. Again, the composition, there are some differences enough so to not account for that. So again, the video that I posted in there actually is a more recent explanation of this thing in here, and actually a more dynamic picture than this one, because it shows you actually the video, it shows you actually what happens step by step. So the early collision was a Mars-sized object, and that Mars-sized object was given a name, actually Theia. So Theia hit the Earth at the right angle. A big chunk of it went to the Earth, actually, and the other one, the biggest part of it, were that got thrown away from the collision, of course, when two things collide, pieces fly every which way. So that started to accumulate the material that was thrown from that impact and formed the current day moon. So that's basically how the collision happened. And that explains the fact that we have enough similarity in structure because the material that was ejected was part of the Earth. And that has enough differences also because the initial chunk was actually from a different object that formed the same region. And that also explains the fact that the moon is actually receding every year for almost 4 centimeters away from the Earth, causing the Earth to slow down in rotation and the day to get longer and longer. So everything fits the bill, okay? So this is the collision theory or the impact theory, and that is the plausible explanation that we have here. So what does it mean to have a theory? So you have observations, and in this case, it's the orbit of the moon, it's the presence of the moon, the fact you actually have it, and also its composition. So you have the data, and you have observations, and now you come up with different explanations, okay? Which explanation fits the bill? That is the one that is actually going to be closer to reality, and that's what's going on in this case. Which prediction actually becomes more true depends on what kind of predictions you can make. Which theory, I should say, is more acceptable is depends on what kind of predictions would you make, okay? If the model really yields that for 3.9 centimeters a year, then that unobserved data that is happening time and time again, and that cannot be explained with anything else. So that again can support that, okay? It can support the presence of this moon and the fact that it's receding. So that's basically what's going on. That's what must have happened for the case of this moon. So for the case of the Earth, okay? Again, in terms of main features, you have the Tycho crater in the bottom. They have also other craters every which way. They're big craters. You have the Marias and you have the highlands. And you have these lines in this case that are emanating from this crater, in this case Tycho crater. And those are the rays that shows the impact and the materials that were thrown every which way in this case. And that left this marks in the form of rays. So this is basically what these things are. Again, Marias or seas. And when you look at the different structure of the moon, you are going to see impact superimposed on the impact, another impact. And that serves actually as a good visual, historical, basically, timeline of the moon. So, and that actually serves for the rest of the planets. So when we look, for example, at Mercury, it doesn't look too much different from the moon. When you look at, for example, Ganymede or Callisto from the moons of Jupiter, they don't look too far from this one. They're heavily cratered, meaning they went through the same events as our moon did. So, and which begs the question in here, what happened to the Earth? Was the Earth exempt from that those events, or Mars for that matter, or any other planet, Venus or anything else? No, they went through similar stuff. But if you look at the surface of Venus, for example, or you can do, very hard to do, but now with the radar penetrating technology through that thick atmosphere, we can. But for Mars, for example, you don't see similar structures like the moon does. So you wonder what happened. Why the Earth, for example, or Mars do not show the same stuff like Mercury and the moon and the other two moons I mentioned before. Why don't they show that? For example, if I look at Io, another moon of Jupiter, or for that matter, even Europa, another moon of Jupiter, I don't see similar features. Well, those objects like Earth, Mars, Io, and all of the other objects must have gone through geological events, weathering, whether liquid water or magma, or for the case of Io, that is, or volcanoes or all kinds of things that erase basically for the most part of what's going on in the surface. So these surfaces are kind of new because they are renewed on a regular basis with geological activity. Whereas the old surfaces like that of the moon or Mercury or Callisto to some extent, and even Ganymede to some extent, they are actually old surfaces. They are exactly what happened to the solar system early on. So they tell you what happened to the solar system from the beginning, because they did not have much activity to go on. So they basically stayed the way they were. No water on their surface, like for example, Mars did for the case of Mercury. So there is no change to the surface, but Mars had water on its surface, and that its features, at least on the surface, looked a lot different than that of the moon. So those, they present you with a challenge, or at least understanding what happened to the solar system immediately when it formed. So it must have been, there was a lot of debris left over from the formation of the solar system, and that debris rained on all of these planets, including the Earth, Mars, and the moon, and everything else. Some of the surfaces that it rained on later on basically erased most of that activity, but the surfaces like the moon and Mercury did not have that luxury, so they left the history basically of what how the solar system was. So that is the early bombardment basically stage of the solar system, and every object, including the sun, by the way, was subject to. Okay, so that's basically some of the stuff that this surface tells us. As a matter of fact, if you look at the surface of the moon, you will see that one side has these features, the other side is really more heavily cratered than the other, than this one. Do I have the other side of the moon? No, it doesn't. But the other side of the moon doesn't have a lot of Marias, which suggests that, because again, the moon is tightly locked with the Earth. So as it rotates around its axis, it's spinning around the Earth. So in this case, what's going on in this case, it's basically giving the same phase, which suggests that the one side of the Earth, the moon actually is thicker than the other side, and the less thick side is the one that exhibits all of these features, because you can get it out, if you wish, a lot easier than that from the other side. And the other side of the moon does not show a lot of Marias like this one does. It's a huge areas on the surface of the moon. Okay. Again, the craters, if you look at the surface of the moon, they're sitting one on top of the other one. So that's suggesting that the older ones are always going to be in the bottom, and the younger ones are going to be on the top. Okay. Again, the highlands must have formed from all of this activity, and also from when the moon had the geology. Again, these are the craters that later on formed this flow of magma. That magma, when it flowed, it basically became solidified later on and formed the dark areas of the moon known as Marias. And if you look at the drop, for example, of water in a bucket, for example, you see the ripples that form. They're not too different from the surface of the moon. So that is basically where the central crater in here is kind of high, then followed by depth, and then followed by another height, and so on and so forth, similar to the ripples that they form. Again, those straight lines that seem to form also in here must have formed later on, because they cross some of these areas in here. And the features of the moon are far richer than basically the simplification that I'm just posting in here. Again, both sides are cratered. The other side is does not show a lot of these features. If you look at the near side in here on the left-hand side versus the far side. And that suggests again a depth of the crust of the moon, as opposed to which side it's facing the Earth and which side is not. So on the side that is facing the Earth is a lot thinner in terms of crust, about 65 kilometers, and the opposite side is almost twice. It's actually more than twice. It's 150 kilometers thick. That's why the surface in here, it does not exhibit a lot of barriers, relatively speaking, compared to the surface that is on the face facing the Earth, because of the fact that it is it's subject to a lot of tidal friction, basically, with the Earth. In terms of the inner structure, this is basically what we believe. Again, it has the crust, it has the mantle, and it has the core basically inside. and it's molten. So there is some sort of a heat that is still coming, but not enough to generate basically much electricity, much magnetic field like the Earth does. For one thing, the moon spins very, very slow compared to the Earth around its axis. It goes 27.3 days to go once around its own axis. In other words, if you were to stand on the surface of the moon, you will have basically 2 weeks of day and 2 weeks of nights, because that's how long the day is on. When I meant 2 weeks of daytime, and 2 weeks of nighttime, basically. That's what I mean by it, okay? The day on it is 27.3 days. So basically that's what that is. So one of the projects some of my students, actually, when we were in another college, they were working on was for the Artemis mission, when people go and live on the moon, and how are they going to get energy from the sun? Because that's the only way, at least at this point, that we know where we can get energy on the moon is solar panels. So solar panel, for 2 weeks, you have no sun. For 2 weeks, you have sun. So you really need to know how to store that energy that you collect from the 2 weeks of exposure to the sun. So that's a challenge. So anyway, this is basically what we think the surface of the, at least the structure of the moon is in terms of the inner structure. In terms of the Marias, basically this is, again, it happened on the thinner side of the crust, more likely, more easily than the thicker side. So when there is a large enough body that hits the surface with a good enough kinetic energy, meaning with a good enough velocity, then that's going to create basically a basin, and that will allow for the magma to flow and solidify, and later impacts will create those secondary craters on the surface. Okay. There is not much atmosphere going on the surface. This is one of the footprints left by the astronauts on the moon. I think this is Armstrong. The point being, no, is it Armstrong or Buzz Aldrin? And one of them. Anyway, the point being in here is that the imprint stayed in its place, and nothing is going to move it because there is no wind or nothing flowing on the surface of the moon. So there is a dust. If you kick it, it's going to basically move around. But that's basically some of the stuff that is typical from the moon surface. Okay, so this is stuff that you know from the dust that is actually forming when these collisions, when these impacts happen. Okay, the last thing in here that we were talking about in here is that the moon rotates, that's 27.3 days around its own axis. And it takes 27.3 days to go once around the sun. Again, we know, and I know some of you probably are sitting in Astronomy 125 and know exactly what's going on in this case in here. You're wondering what happened to 29.5 cycle, and we talked about that one actually. That is the lunar month or synodic month, versus the sidereal month, the actual rotation of the moon around its own axis, which is 27.3 days. So the moon is tidally locked, and as I was saying before, the moon actually was closer to the Earth. At some point, the day was a lot shorter than what it is today, and it's going to get longer and longer as the moon recedes further and further away from the sun, from the Earth. In all times, it's going to stay that tidally locked. So as it moves away, it's going to spin slower, and it's going to, the Earth is going to actually spin slower on its axis also, and that is the conservation of energy. One thing that you really need to understand also, this tidal locking also loses energy in a different form, because when the moon is actually, let me draw something in here to hopefully understand this point in here. Let me get this picture to see it, okay? Let me share quickly, and this is going to be the last point today. Share. So let me explain this point in here quickly in here, because it's very important to understand actually the tides. So here is the Earth, here is the moon, okay? The Earth is spinning, the moon is spinning around the Earth. So the Earth is spinning around this axis, and the moon is going around the Earth, okay? Now, because of force of gravity, the moon pulls on the Earth, and the Earth pulls on the moon. The Earth has a surface that is mainly water, and the water is actually going to be attracted closer to the moon. So in this case, you have the tide, okay, on this side. But because the moon is pulling on the Earth, as the Earth displaces basically the center of gravity due to this force, is going to leave behind also another tide. So you have another tide on this side and another tide on the other side. And that is the two bulges. That's why actually half a day later, 12 hours later, the moon is going to be on, or at least because the Earth is spinning. So you have to understand this, okay? So the moon is only one side because it takes 27.3 days. So this side of the Earth will move in here, and this side of the Earth will move in there. So the picture looks like the moon is actually going to be on the other side. But don't forget, the moon is hardly moved around the Earth. So the moon is on one side. So the side that had the other tide, which was a kind of an inertia tide, now is actually a real tide because it's being pulled closer to the moon. So, and the side that was actually being moved in here is going to be on the other side. So this is about 12 hours later. That's why in a 24-hour day, you will have two tides per day because of this phenomenon. Now, tides are not just caused by the moon, they're caused actually by the sun also. During a full moon, for example, or new moon for that matter. So during a full moon, here is the sun. The sun is very, very far away from the Earth, relatively speaking, compared to the moon, okay? Again, look, but it's bigger, so it has a little bit of effect, but not that much. So the sun is pulling, this side is reacting. So there is actually a bigger tide, and also this side is pulling from the moon. So the moon is pulling, and this side also is reacting to the sun. I'm exaggerating in here a little bit the voltage, okay? The sun effect is a lot smaller than the moon's effect. The moon effect is a lot bigger because it's closer. But the point being in here, you have the tide that becomes bigger. This tide is called the spring tide. So there are times of the year, excuse me, where tides are so big because of the combined effect of the Earth and the moon. Obviously, this side is a low tide during the same time when the other sides were experiencing high tides. And I should say here, because remember, the Earth is a spherical object, so there is a sphere in here, okay? So the regions on this side and the opposite side, they're experiencing low tides, okay? I don't mean the North Pole and the South Pole. I mean the same equator, okay? We're talking about the same more or less region, okay? If you are, for example, near the ocean, you're going to experience a low tide, high tide, a low tide, a high tide in the same day, okay? Sometimes they are spring tides because they are a combination of the two. Versus neap tides. Neap tides is when they are actually canceled. The two effects are canceled. So, and this is usually happens in a quarter moon. So again, the moon is pulling on one side, but the sun is pulling on the opposite side. Albeit in here, the effect is a lot less than the moon, but it's still nonetheless. So the tide in here is going to be the smallest. So this is how the tides form actually, and it's because of the tidal locking of the moon. And this effect basically is due to the presence of the moon for the most part, and actually the sun too. So this is in a nutshell, this unit, at least unit 38, okay? And we still have more stuff to talk about unit 41, which is actually a very important topic. So we're making our way toward the solar system actually. So hopefully we'll have all of the topics covered. Sounds good? So I'll see you guys Wednesday. For those sitting in the lab, I'll see you guys on tomorrow, okay? And I'll try to post this recording today, okay? Thank you.